All right, so tonight we get to do partial fractions. So let's look at this first integral right here. So we're going to ignore that integral for a minute. Let's look at this integral right here. So the way that it's set up, we can do the integral, we can actually just split this integral in half. So we can take the integral of 2 over x minus 1 minus the integral of 1 over x plus 2. So what that allows me to do is just to do that simple integration. So the first thing is I can take out that 2. So now I have just 1 over x minus 1 dx. Let's just look at that first one first. If I just do a simple u substitution and make u x minus 1, du is just dx, right? Because the 1's going to disappear completely, and the x is going to become a 1. So this is just 2, 1 over u du, which is 2 ln, and then I'll substitute back in so I don't have to worry, plus 6. So it's the ln of x minus 1. And then if we did the other one, same thing would happen, right? So I'd have the integral of 1 minus x plus 2, same thing. U is x plus 2, du is dx. So it's just the integral of 1 over u du. So this side right here becomes just the ln of x plus 2. So this answer is 2 ln x minus 1 minus ln x plus 2 plus c. So the way that it's broken up, it's pretty simple to do with just a simple u substitution. Any questions on how I did that one? Yes, it would be nice if everything stayed that simple, but that is not the way of life. All right. So now let's look at this integral. So sending it back in. So this integral, I can't split up. So I could split up and make this the integral of x over x squared plus x minus 2 plus the integral of 5 over x squared plus x minus 2. I could do that. However, I can't make, so actually in this one, I could do a substitution in this one, but I could not in the second one. Because I could make u the whole bottom piece, which would be just 2x, and I could do a simple u substitution on the first one. But the second part I couldn't. So we need to figure out a better way to do this. So
wait, why couldn't you do it with the second part?
Because I can't make the bottom u. Because if I make u x squared plus x minus 2, du is 2x dx. And I don't have an x in the second one to do it. The first one, I'd have that x, I have the x and the dx right there that I can do. But in the second one, I don't have the x that I'd be able to do. So that the problem comes in is like, okay, I've got to come up with some other way to do this. So I'll show you something really cool. Let's take the original problem that I did a second ago. Let's take these two fractions and put them together. So if I'm going to take two fractions and I want to put them together, what do I need?
A common base.
Yep, need a common denominator. So in simple problems, like if I had 3/4 plus 5/8, I would just make them both 8 and do it. If this was, say, a 7, I couldn't make it a simple number, but I could just multiply the two bases together. And that's what a lot of times people will do. That's what we're going to have to do in this problem. We're going to multiply the two bases together. So my new base is going to be x minus 1 and then x plus 2.
So does that mean we're just gonna end up using factoring on the first problem?
Similar, yeah. We're going to have to factor it, and then we're going to have to do something for the top. Because to get the top isn't just 2 and 1. So there'd be the 2 times x plus 2 minus 1 times x minus 1. So my top part, huh?
Clever.
So this one is just 2x plus 4 minus x plus 1, which if we combine those gives me x plus 5. And the bottom, if I filled it out, would give me the x squared plus x minus 2. So this problem right here is the same as that problem. The question comes in is, how do I go from this to that? It's easy to add two fractions together. It's harder to split two fractions up in a very specific way. Okay, that's what we're going to actually look at tonight. So let's actually look at this one. We'll do this one first.
So both of the parentheses in the denominator are also found in the numerator.
Yeah, because when you find the like base, I have to multiply the numerator by the piece that I'm multiplying the denominator by to keep the fraction the same. So
I'm
like
just
that
trying to-
so like this first fraction here, I multiplied by x plus 2 here,
Yep.
and then the bottom was the x plus 2 there to keep them the same.
Gotcha.
So that's how that one went up in the numerator. And that's the hard part. It's like, that's the piece that like we'd have to figure out what we're going to put up there. The nice thing is this part is in the denominator, so we know that part. The tricky part is figuring out what these numbers out here are going to be to give me that problem. That's the piece that we have to figure out, is what are those numbers going to be. So we've got x plus 5 over x squared plus x minus 2. All right, so the first step we're going to do, the first thing is we're going to factor the bottom. So as we already saw in the last one, it's x plus 2 and x minus 1. All right. So the first way that we're going to do this is I'm going to basically what I want is I want something that has a number up here and x plus 2 down the bottom. And then I want a number up here and x minus 1 down the bottom. So my goal is to figure out what those two numbers are going to be. I know that the top has to end up being the x plus 5. Like I know that top part, when I put them all together, has to end up being the x plus 5. So I have A x minus 1 and B x plus 2 equals x plus 5. So I have ax minus a plus bx plus 2b equals x plus 5. That part makes sense? All right, so what I'm going to do is let's look at the x's. So I have a plus b x, and that has to equal x. And then I have negative a plus 2b, that has to equal 5. So if we look at this, I can eliminate the two x's here and just say it equals 1. So a plus b equals 1 and negative a plus 2b equals 5.
Wait, how did you figure this out too again?
All right, hold on. Let me actually, I'm going to go a little. So let me go back a step. All right, so do you understand where I got this from?
Yeah.
Okay. So the next step was I just distributed it. So ax minus a and bx plus 2b. So I just distributed it. Now I'm going to put the x's together and the numbers together. So I have ax plus bx and negative a plus 2b. So this right here with the x's, the a plus b, has to equal my x piece. And my negative a plus 2b has to equal my 5. Because in essence, those are the coefficients numbers that are at the end. Still good or no?
Yes, I'm just wondering, in a typical algebra problem, would it be okay to just pull out everything that relates to X?
Yeah. Because we're basically, what we're looking for is we're looking for the coefficients. So we're not actually in this problem, like I've got this whole thing here. We're not really solving it for X. We're not solving it for a single number. We're looking at the coefficients in front of these things because that's the goal. I'm looking for those two things and I'm trying to figure out an A and a B that's going to make that happen.
Gotcha.
So in essence, what we're about to do in a second is a system of equations. So I've got a plus b has to equal 1 because that's the coefficient in front of my x. And then negative a plus 2b has to equal 5 because that's the number that's by itself.
I really don't understand how you went from that third line there, the third equation, to the two fourth equations still.
All right. If I change, hold on a second, let me just change one thing. I'm going to change a couple of things here. Okay. So I changed one little thing in this just to make it a little clearer. So basically, if my left and the right side of my equations are equal to each other, right? Because they're an equal sign there. The number that's in front of my x has to be equal to the number in the front of the x over here, correct? For this to balance out. So that's how I got the a plus b equals 1, because the a plus b has to match the coefficient in front of the x on the other side. Otherwise, it wouldn't balance.
Yeah, I'm not sure if I'm seeing that correctly or not, as it still doesn't make too much sense.
All right, let's try another explanation. All right, so let's go back to this. So if we look at this step here, so this was the original problem when I basically said that this and this are the same because I multiplied it out, correct? So in this problem, I have the x plus 2 and the x minus 1. However, in my problem that I'm trying to solve, I don't know what these two numbers are. So that's the A and that's the B, because I'm not sure what those are when I'm doing the problem. Okay, so if I'm going backwards, I'm not sure what those are. So I've got to come up with that piece. So the A and the B are going to be numbers, but those are my coefficient pieces of it. So this whole top piece right there has to equal the x plus 5. That you get?
Yes, that part makes sense.
Okay. So if we're looking at trying to balance this equation out, normally when you're looking at them, you only have one thing on either side. Like, so I would have just an x or just a number over here. So, and we would be solving for that. The problem is in this problem, I have 3 variables. I have A, I have B, and I have X. So we can't solve this equation the way that it's set up right now. So what I'm really looking for is I'm looking at the coefficients in front of those pieces over there. So I'm looking for the coefficient in front of the X. I'm looking for the constant term at the end. And I'm saying, okay, what does the A and B have to be to make these two sides identical? So when I distributed the A through and the B through, I had the AX and the BX. Those both have X on. So that becomes that A plus B of X.
I
So
see now
somehow-
you're setting each variable like kind of equal to it. So like the 5 matches up with the negative A plus 2B because that's just a number, not a variable. And then the A plus BX relates to the X because it's an X.
Correct.
Okay,
Exactly.
that makes a lot more sense now. Thank you for explaining that.
No problem. That honestly, that's the biggest part of this entire process that we're going to do tonight. So I have no problem going through and making sure you understand that piece, because that's a big deal. So, all right. So now that we've got those two equations, we're going to do a simple system of equations. Remember, way back in algebra, systems of equations, a few different ways to do it. One of the ways was called linear combinations, where we can take the two equations and add them together to get rid of things. So A minus A is gone. So I have 3B equals 6. So B equals 2. Now that B equals 2, I can now figure out A. So if A plus 2 equals 1, A has to be negative 1. And there's my A. I'm going to show you another way in a little bit to do this without systems of equations. For those of you who do not remember how to do systems of equations very well. But this one works out really easily with systems of equations because the A's cancel out. All right, so
Just a coincidence that when you first wrote that down, that we had the answer, because when you first wrote it down, it was A plus BX equals X, and A plus B sorry, and negative a plus 2b equals 5, and the answer was x plus 5.
Yeah, that was the goal. Yes, that's because that's the way that it worked. You want those numbers over there. So yes, that wasn't a coincidence at all. It was on purpose. So when we look at this one now, A in this case was -1 and B was 2, which was the exact same thing as my original problem, because the 2 was over the x minus 1 and the -1 was over the x plus 2. So putting fractions together, pretty simple. Taking fractions apart, a little more complicated. All right. Look at,
It seems like the integrals for these problems are going to be a lot easier than the other ones that we've been doing. Is that going to hold true continuing, or is that
yeah,
just
actually as crazy as it sounds, the integration part and all these problems that we've done so far, even the integration by parts is a little more complicated, like there's a little more steps there. But honestly, all these methods that we're looking at, the integral part actually isn't the hard part. It's getting it into the format that you need to do the integral. That's the hard part. So like all the stuff that we just did to get from this to this, that's a lot of work. Once you get to this, the answer is easy.
yeah, because it's just a simple U substitution, like you've been saying. So it's like
Correct.
not
But
very
the
hard.
hard part is getting to there to do it. And that's where the algebra comes into play. That's why I've told people for a long time, I think pre-calculus is the most important class for calculus. It's like to really understand your algebra before you come into calculus, because all the errors I see made are in algebra, not the actual calculus concepts. As you're going to see in this problem, because I'm going to have you do something that I guarantee you haven't done in a long time. All right, so we just did one problem where we actually came up and had to do the partial fractions, and we're going to do a couple more of those in a minute. But there's one other thing that we want to do before we even have to look at partial fractions, is if the denominator is smaller than the numerator of the degrees, the first thing we have to do before we do any work is long division. We want to,
Excuse me, sorry to interrupt. For the sake of completion on the previous problem, we just finished doing the integrals using du.
I did, it's right, oh, hold on, I go back. I did already, actually. It's this. It was the very first problem I did.
Wait a minute, but what about the numerators?
The numerators are there. That's this problem right here. The very first problem I did is the same as this problem. Once you get back to the 2 and the -1, which we got here, it's the same problem that we did at the beginning. So this would be the integral for it with the U substitution.
Got it. Okay.
That's why I did that first, because I wanted to show you that the integral part's actually pretty easy. It's just we have to get to that point to actually do it. All right. Okay, who remembers long division? When I teach this in high school, I make them actually do long division from like actual simple numbers. And it's amazing how many kids have no clue how to do it. All right, so long division. The denominator is on the outside. That's and the numerator is on the inside. When you're doing it, you always want to put in zeros for everything you're missing. Just like dividing in like thousands and stuff like that, zeros are my placeholders. So now we're going to divide. How many times does x go into x to the third?
3.
Twice. So in essence, we're multiplying. So it's what times x is going to give me x to the third. So that's where the x squared is. So the way I said it, 3 makes sense, but yes. So now we multiply. X squared times x is x to the third. X squared times -1 is negative x squared. We change our signs. And we bring everything down. First thing's gone, x squared plus x plus 0. X squared, x times what's going to give me x squared is x. And we multiply. Change my signs. Now I divide again. Change the signs. So I have a remainder of 2. So this problem. All right, so first thing before I go on to the next thing.
Oh, wait a minute. Sorry again to interrupt.
That's okay.
What's why do you minus there? Like I just don't understand how you're doing the long division. Like
You're always subtracting. Once you figure out what it is, you're subtracting it off to figure out what's left. So even like if we do a simple one, like actually this is not, I'm only going to do one step on this because I'm literally making the number up off the top of my head. 9, 7, 3, 1. How many times does 32 go into 97? 3 times, which gives me 96. And then I would subtract that to get the 131.
okay.
Okay, and then I would do again. 32 goes into that. How many times? And actually, it's 4 times. So then it's going to be 128, and then I subtract it and 3, and then that would be my remainder. So it's always subtracting off what you have to find the next piece. So the same thing with you doing with variables. That's why I was changing the signs, because it's simpler to change all my signs than to remember to do the subtraction of negatives. So I always just change the signs, and then you're basically just adding down.
The thing that had confused me that I think he might be getting stuck on too, correct me if I'm wrong, when you put x squared up at the top, you multiply that by x minus 1.
Yes, yep. So I took that and multiplied it by this to get this. That.
Because that's where I got stuck. And then because you're subtracting, you flip the sign of the second.
Yeah, you're flipping both signs basically. Make the first one negative because it was already positive, and then change the sign to the second one. Yeah.
I was about to ask a similar question, but I got it cleared up now.
Awesome. I have to say, you guys actually ask really good questions. So keep asking. I was telling somebody the other day, this is my best online class that I've had because you guys are actually asking questions and I'm not just talking to myself. All right, so we're good with the long division part? Kind of. All right, now let's actually look at this in terms of an integral. So I'm going to rewrite my integral. The top part's going to go first. And then the remainder part is the last part. So it's 2 over x minus 1. Dx. So when you have the numerator on top has a higher degree than the bottom, you want to do long division first because you might not have to do partial fractions. And in this example, we're not going to have to do partial fractions. We've split the problem up in a way that I can just do my integral right from what I have right now. So x squared becomes x to the third over 3. X becomes x squared over 2. The 2 becomes 2x. And this one right here, the last part here, this is where we're going to do that u substitution. But if you start to look at them, so if I make my u x minus 1, du is dx, that just becomes, the integral of that just becomes ln of u. So this problem right here becomes 2 ln of x minus 1. And I'm running out of room. There's a plus c on the after the screen's over.
It's important to remember that it's the absolute value of x, right?
Yes, because we cannot do a log or a natural log or a logarithm of a negative number.
Wait, why? That might be the question.
So because a natural log is the inverse of an exponential function, and the exponential function does not have any values that are negative unless it's shifted. So the actual range of an exponential function is 0 to infinity.
Right, because it only gets smaller and smaller and smaller. It doesn't actually
Right.
have a negative value.
Correct. So since the ln is the inverse of that, the domain of a natural log or a logarithm has to be positive.
Okay.
All right. And this little u rule with the ln, I wouldn't sit there and keep writing them out. It's one of those ones that after you do it a couple of times, just recognize that as long as the base or as long as the denominator is a linear function, you do not have to worry about it. That's going to be gone. It's just going to be ln of that number.
And this is, we do the long division when the numerator is magnitudes bigger or orders bigger than the denominator, right?
Yep. Anytime the degree of the numerator is bigger than the denominator, you do long division. All right. So that's the first thing you always want to look for is long division. Okay. So this is the official, so there's actually 4 cases that we're going to look at, or 3 cases, sorry. Yeah, 3 cases. Nope, 4. There's 4. The key part to all these is figuring out how we're going to break them up. All right. So the first ones we're going to look at is ones that I can break up all into linear functions. Because as I just said a second ago, if they're in linear functions, I can instantly be able to just do the simple ln integration and get the answer that way. So that's the first thing we want to look at is, can we break them down so that they're all linear functions in the denominator, or linear factors in the denominator. So all this mess is going to look a lot easier once I actually do one. All right, we'll look at one. Okay, so here's the problem. The first thing we have to do always, so look at this one. So my degree on the top is 2, the degree on the bottom is 3. So I do not have to worry about long division in this problem. So the first thing I'm going to have to do is I want to factor the denominator. So we've got 2x to the third plus 3x squared minus 2x. So I can pull an x out of the whole problem. So I have 2x squared plus 3x minus 2. And then if we factor that, we get 2x minus 1 and x plus 2. I'm going to ask a question, and don't feel bad if you say yes. Does anybody want me to actually show you how to factor that out? Or is everybody good with the factoring?
Yes, please.
Okay. I actually do this slightly different than most people do it. But I think it actually works out really nice. I actually do what's known as factor by grouping on this problem. So I'm looking for two numbers that multiply to -4 and add to 3. Okay. So basically all I do is I take the first and last number and multiply them. That's how I got the -4. So two numbers that multiply to -4 and add to 3 would be 4 and -1. So I'm going to split this term up in the middle. I'm going to do 4x minus 1x minus 2. And now I can pull out a 2x out of this side, and I'm left with x plus 2. And I can pull out a minus sign from that one, and I'm left with x plus 2. This thing gives me the x plus 2 and 2x minus 1.
Wait, how did you do that first split, Professor? You said
So,
two numbers that
I'm looking-
multiply to -4
Yeah.
and add to 3, right?
Right. So basically, I'm looking for two numbers that multiply to -4 and add to 3. So if you think about it, if we took these two parentheses and FOILed it out, if I just FOILed this really quick, the goal is to get, so that's 2x squared plus 4x minus x plus, or sorry, minus 2. Minus 2. The goal is to get that. So if you're foiling, that's your first step, is when you have 4 terms. So my goal is to get that to give me the 4 terms so I can figure out the factor part. And that works by looking for two numbers that multiply to the multiplication of those two, the 2, -2, and add to the middle term, which is probably how you were taught how to do it with when a is 1. You were looking for the numbers that multiply to the last number and add to the middle number.
I feel like
Yeah.
it's been so long since we've done this.
I know.
Oof.
I know. That's what, honestly, that's what makes this section hard. It's not the integral. It's all the algebra that's in this section. It's long division, it's systems of equations, it's factoring, which you don't practice enough.
I graduated high school in 2012, man.
Yep.
So wait,
Yeah, same year for me.
but I get the idea of like they have to multiply by -4 and add to 3, but there's a million numbers that can do that. So that's what I'm
No.
wondering. Like,
No, there's not. That's actually the most important part. You're looking for because we're looking for a multiple, there's very few numbers that would work. And actually there's only one number, only the pair of numbers that will ever work actually in this problem. So if we were looking at two numbers that add to it, you're right. There's millions of combinations. But since we're looking for two numbers that multiply to -4, first of all, we're not dealing with fractions and decimals, because yes, there would be a bunch of them if we dealt with that. Since they're all whole numbers, there's only a limited number of possibilities to get to 4. And actually, in this case, there's only 2. It's 4 and 1 or 2 and 2. So that's why this method works, because there is a very limited number of multiples that would work. And then you just figure out which one adds to the number you want. And the other nice thing is you can check this problem every single step you do. So like 4 minus 1 is 3. So that works. If you distribute here back, you're going to get to that step above it. So you can figure out if you've made a mistake by checking your work at every single step in this process. Don't worry, it's not the last one we're going to factor today. So I will do a little more factoring in the other ones too. But I do want to actually finish like at least the partial fractions for this one. All right, so this problem, when we're doing partial fractions for when they're all linear terms, we're going to split this up. So it's a over x, b over 2x minus 1, and c over x plus 2 dx. All right, that part makes sense and how I split it up. So now my a is going to be multiplied by 2x minus 1 and x plus 2. My b is going to be multiplied by x and x plus 2. And my c is x and 2x minus 1.
So just so I'm not confused, the A, B, and C are basically the relations of the ones not in the denominators.
So the a, b, and the c would be whatever the numbers at the top are going to be. So I get, in essence, the x squared plus 2x minus 1.
Yeah, okay, okay, that makes sense.
So you're multiplying. Yeah, when you're going backwards, I'm going to multiply by the ones that are missing from underneath that one. So yeah, that's why the x is the 2x minus 1 and the x plus 2. All right, so here is my equation that I have. X squared plus 2x minus 1 has to equal those three things added together. Now, for all the years that I've taught this, I know for a fact the majority of people do not know how to do systems of equations very well, especially once they get past two variables. So there's another way to do this. Okay. If you look at the pieces that are there, if I plug in certain numbers, things are going to disappear for me. And I'm going to be left with just one letter left. Okay. So I'm going to take, and I'm going to say x equals 0. You actually can pick any numbers you want, but only certain numbers are going to make your life easier. And hopefully, as I do this, you're going to start to see which numbers are going to make your life easier. So I'm going to say x equals 0. Now, everywhere above on the screen, I'm going to plug in 0 for the x. So for this first one, this side I have -1 equals a times -1 times 2, and that's it. So by plugging in 0, that's what I have left in this problem. So I have -1 equals -2a. So 1/2 equals a. Next one I'm going to plug in is -2. So on this side, I get 4 minus 4, or actually I also have, this is also -1. And then I have C times -2 times -5. So I get -1 equals 10C. So C equals -1, 10. And my last one I'm going to plug in is 1/2. So when I plug in 1/2, I get 1/4. Yeah. Equal B times 1/2 times 3/2. So I got 1/4 equals 3/4 B. Wait, hold on. I think I screwed something up. I did screw something up. That's 5/2. So B equals 1/5. Okay. Who wants to tell me where I came up with my 3 numbers?
Magic, or you could have figured out what makes 0 for each of the individual parts.
That's better.
There's a couple other options you could have picked for some of these, I guess.
Um,
I think for
Actually-
one of them, there was.
because your goal is basically these are the 3 roots for my denominator. The goal is basically to get things to disappear. So whenever you're multiplying something by 0, it's gone. So when I put in the 0, that right there and that right there became 0. So they're gone. So the only thing I have left is my A. When I plugged in -2, that right there and that right there disappeared. So all I had left was C. And then the 1/2 got rid of that one and that one. So on this one, and there's going to be certain situations where we look at that the roots aren't going to help me. I got to pick some other number. Or once you get 2 values, then you can use that to figure out the third one. But if you have the roots, use those and they will eliminate things that you can get. So that's actually where those 3 numbers came from. They're just the roots, not total magic. They were
That's just
just
because it worked out where it would get it out of the left side too, but I can't imagine that's gonna happen with every equation. I think this was kind of a baby layout.
Actually, no. So the left side, I actually plugged those numbers in. So like it just happened to work out pretty easy to do in my head. So like the 0 one, yeah, you were just left with the 1. The -2 squared is 4, and then it was -4, and then equals -1. So you plug those numbers into the left side, they just happen to work out fine. But it doesn't matter which number you plug into the left side, you could have calculated it out. It's really the right side that you're looking at because that's the one that has all the extra letters that you want to kind of get rid of to solve. So like that's where the 1/4 came in the bottom because I have 1/2, the 1/4 is the 1/2 squared, and then 2 times 1/2 ended up giving me 1. 1 minus 1 was 0, so that was just the 1/4. So, but yeah, the left side you can plug anything you want in there. It's really, you want to choose numbers that are going to help you on the right side of the equation. Oh. Where is it? All right. So now we have A, B, and C. So I can plug in my A, B, and my C up here, which is going to give me this. So the integral of the first one is just 1/2 ln of x. Oh wait, sorry. I think what was it? That wasn't a negative sign. I missed it. The integral of the last one is -1/10 ln of x plus 2. And everybody's going, wait, you missed the middle one. Yes, on purpose. So this one, the 1/5 is going to come out, but then you have, so we have this. We have 1 over 2x minus 1 dx. So if u is 2x minus 1, du is 2 dx. The 2 doesn't vanish. So because there's a 2 there, I got to bring it over. So this is 1/5 times 1/2 ln of 2x minus 1. So it's 1/10 ln 2x minus 1. So in essence, whenever there's a number in front of your x, that's going to get pulled out as a fraction.
Professor,
Yeah.
so I was really kind of trying to utilize the same kind of systems of equations there to kind of make that factoring of that problem easier. Are you able to work it out so that it's not just like in our head, but it's like a system of equation like that you added together? For example, that earlier factorization you mentioned, right? Because we have a 2 in front of the x, right? Then it's kind of like 2a plus b has to equal, you mentioned 3 plus b needs to equal 3. And then a times b, excuse me, 2a times b needs to equal -4.
Yeah. Okay. So here's what happens. If you were going to do this with system of equations, all right, this is what you're going to end up getting. If you were going to do this out with systems of equations, that's what you'd end up having. Because So I'm gonna actually give, because they actually did it with systems of equations in the book, so I'm literally copying this from the book because I don't want to write it all out. But I will explain what it is. So we start off with, so this part right here is the exact same thing we had before. So by doing the distribution and multiplying it all out, you end up getting 2a plus b plus 2c equals the x squared. Is part is
Oh,
the
no,
part-
definitely not trying to do this with systems of equations. I think the method that you mentioned is
Yeah.
easy. I'm talking about going back to getting the factor of, or factoring 2x squared plus 3x minus 2. Are you able to kind of quickly draw out that systems of equation approach to figuring out those coefficients? Yeah, right there on the second line when you,
Oh, this?
yeah, are you able to do that systematically rather than in your head for us, please?
Yeah, I did. You missed that. I did do that. I could do it again. Give me 1 second. That's fine. Let's see. So hold on. Let me just write the equation down and I'll do it real quick. So 2x squared plus 3x minus 2. So find two numbers that multiply to -4. This is what you want me to do, right?
But I want it systematically, right? So like we need a plus b, right? Needs to equal -4, or like the same system of equations approach that you utilize.
Oh, no. So, okay. All right. Here's the problem. Okay. Now I got what you're saying. To go from here to here, that is not systems of equations. We never did systems of equations to do that.
Can
So
you?
go from, to factor it, we didn't do systems of equations.
But can
We
you?
use systems of equations to find the a and the b to figure out the coefficients up top, to find these things original in the other problem, not to factor it.
I know, but can't you use systems of equations to figure out those coefficients? It seems like a very basic application of systems of equations.
I don't know. I've never actually tried to do systems of equations to factor.
I mean, but you did just kind of figure out what they need to be, right? It needs to be coefficient A, right? 2a plus b needs to equal 2a plus b needs to equal 3, right? So a 2a plus b.
Could
needs to
you?
equal 3.
Yeah, the problem is okay, so here's the problem. Yes, you probably could, but I don't know why you'd want to. It's probably harder. Because again, you're gonna find out the two numbers to split it to, but then you still have to do this extra step to factor it. You still are gonna have to do all the rest of the steps that I did. It's all you're doing with the method you're trying to do is come up with 4 and -1, which I think is gonna make your life a lot harder.
Well, the thing is, sometimes they're not so evident.
Unless they're fractional, you're gonna find them pretty quick. I think it's been a while since you've done them, so it's like if you try a few of them, trust me, you'll actually come up with those numbers pretty quickly. All right, just because I know I'm gonna run out of time if I don't get through the rest of these. I can work after the class and I can do a couple problems and I can show you why that'll work out faster. Because I can make up those problems pretty quick. All right, case 2. If any of your linear factors are repeated, we need to take that into account. And you can't just use the factor again, because if you just use the factor again, it'll cancel that out and it won't help me. Because if I just put x minus 1, x minus 1, x minus 1, that's all the same fraction at that point. And I'm not going to end up getting the x minus 1 to the 3rd power. So when you're doing them, you're actually going to write them out multiple times with those exponents. So it's not going to make my integration any harder. It's actually pretty easy to do. These you don't even need to use LNs for. It's just going to give us more variables that we're going to have to find on the top, more coefficients. That's really the only extra piece that we're going to have to do there. So let's do one. so you can see. There. So, all right. Step one. What's the first thing we always got to look at?
Degree higher in the numerator.
Correct. So we have to, so in this case, we're gonna have to do long division. So minus x plus 1, x to the fourth plus 0, x to the third minus 2x squared plus 4x plus 1. All right, so what do I got to multiply x to the third by to get x to the fourth? So then I multiply x to the fourth minus x to the third minus x squared plus x. Change all my signs. So I get x to the third minus x squared plus 3x plus. Do it again. Fine. So I'm left with 4x. So my new integral is this. We have the x plus 1. And then my remainder was 4x over my original denominator.
Just real quick, the x plus 1 is what we got when we
Yeah, that was the that was the
all right, just making sure.
Why is
Function.
it plus 3x? Oh, never mind. Sorry.
That's okay. Yeah, that's the quotient. That's the remainder. All right. What's the next thing we have to do?
Back to the bottom.
Back to the bottom. So let's do that next. So I've got x to the third minus x squared minus x plus 1. This one happens to already be in terms of 4. So if there's 4 of them, just split it. I can pull out an x squared on this side, x minus 1. I can pull out a negative 1 on this side, and I'm left with x minus 1. So that's that.
Professor, could you go back to the previous page real quick on the long division side?
Sure.
So yeah, when you add the 1 there, it starts, when you add the 1 and you multiply it by the, minus x squared there, then you'd be, oh, gosh, okay, so sorry. Sure.
It's okay.
Also, thank you.
All right, so we've got that. But we're not done. Because x squared minus 1 is the difference of two squares. So that's x minus 1, x plus 1.
And now x minus 1 repeats.
Huh?
So now we had x minus 1 times x plus 1 times x minus 1.
Right. So we have x minus 1 squared, which is the important part of this problem. So we have x minus 1 squared times x plus 1. So, because we have this x minus 1 and that x minus 1. So this is going to go to this problem. So we're only going to look right now at that part right there. I'm going to ignore the x plus 1 for a minute. So I have, so that part's going to become a over x minus 1 plus b over x minus 1 squared plus c over x plus 1. That's how we split that one up.
Okay.
So where did
that's-
that
Yeah.
singular x minus 1 come from?
So it's when you're doing, that's the actual process. So when you're doing out factors when they're repeated, you have to do every power of that one. So you can see how this one's x minus 1 to the third. I have x minus 1, x minus 1 squared, x minus 1 to the third.
Okay.
Okay.
And so
Otherwise, yeah, go ahead.
that would determine how many numerators we had. So then it could be A, B, C, D, E, F, G if it was x.
Oh
to
yeah,
the
I can
third.
keep going. Yes.
Oh,
Don't
And-
worry. You are not going to have anything that long on the test.
And with that, that's why there's a of x, a over x, and then plus a b over x squared, because x squared.
Is squared.
Yep. All right.
Yep, same concept for that one. So yes, actually in the book, they have one that went A through E, and it literally goes, yeah, we're not going to do this. Use a computer. So yeah, you're not going to have one. Honestly, I think the longest one you're going to see is 4 letters, and even that one's not going to be that difficult for you to figure out. So. All right, so now we have to do our coefficients to figure out what we're going to get from this one. So I've got 4x equals a times x minus 1 times x plus 1 plus b times x plus 1 plus c times x minus 1 squared.
so up to this point, there's always been 2 things that we multiply by. Now there's only 1.
What do you mean?
So in the last few problems, to get the denominators to be the same, we had to multiply by 2 things. This time we're only multiplying by 1.
Kind of. So because like in this first one, actually the A I did, I multiplied by x, the other x minus 1 and the x plus 1. The B, I only had to multiply by the x plus 1 because I already had the most of the x minus 1s there. And C, I did multiply by 2. It's just x minus 1 squared. I just didn't put the other, I just didn't split it up. So
Okay.
Could you say that again? Why are we multiplying a times x minus 1 squared?
I'm multiplying because I already have an x minus 1 there. So it's kind of the concept of if I have 1/4 and 1/8, and I'm looking for a common denominator, I don't need to multiply the 4 by 8. I'm only multiplying it by 2 because that's the thing that's missing. So in this one, in A, I'm only missing 1 x minus 1. So that's why I decided to multiply by that one other one. All right. So let's look at this one. So if I'm going to, so now, again, remember, we're looking for numbers that we can plug in to get rid of things. So in this case, I can plug in 1 and things are going to disappear. So on this side, I have 4, the A is gone, and the C is gone. So this is just going to equal B times 2. So B equals 2. And then I can use -1 for the exact same thing because it's going to get rid of my +1 ones. So I get -4 equals, so the A is gone again. The B is gone, and C, -1, -2 squared, which is 4. So C equals -1. So far, so good. So in this one, I don't have another number that I can plug in to get rid of things. So what's the easiest number in the world to plug in?
0.
0. So this is going to be 0 equals A times -1 times 1 plus B times 1 plus C times 1. So 0 equals A plus B plus C. But I already know B and C. Oh, I forgot the negative sign in the A. So A equals a +1. So if you run out of numbers to try an easy number. The only thing that's going to happen is you're going to have multiple letters left over, so you have to use what you found in the other ones to solve it.
Sir, how did you like if you choose like x equals 1, how do you know like which one to put it into? Like for x
You're putting it
equals,
in all of them. So when you plug in x equals 1, you're plugging it in every one. So this is 4 times 1. This is A, 1 minus 1, 1 plus 1. The thing is, what's 1 minus 1?
oh, okay, I didn't see that.
So that's, yeah, in essence, you're plugging it in all of them, but it's going to cancel out the ones that it's going to cancel out. The only one that didn't work, so in this case, the only 2 numbers that I could use to do that were 1 and -1 because those were the ones, my factors, or my roots or my zeros, whatever you want to call them in this problem. I needed another number to come up with the other letter, and I just chose 0.
Okay, so we start with the roots, and then we're going to use 0. Now, what happens when 0 fails us?
You could technically try any other number you want. But if you already have, like most of the situations you're gonna have, you're gonna be able to find at least a couple of the numbers without getting to zero, because you're gonna be able to find the factors. Once you get to the 0 point, you're gonna have enough of them that you can use those numbers to plug in.
Okay,
So that's why the 0 worked. The 0 didn't work because it worked. The 0 worked because I already had B and C. All right. So we go back to my original problem. So my original problem was x plus 1. And now I split up my thing. So my A was 1. So I have 1 over x minus 1. And then I have 2 over x minus 1 squared. And then I have negative 1 over x plus 1. So that's what I have. All right, so now I can do my integral. So the integral of x is x squared over 2. Integral of 1 is x. 1 over x minus 1 is just the ln of x minus 1. The one with the squared, so if I just do that quick integral here, the integral of 2, so the 2 can come out front, so we'll just take this 2 out front real quick. So it's 1 over x minus 1 squared. So my u will be x minus 1. So du is just dx. So this problem becomes the integral of 1 over u squared, which is u to the negative 1 over negative 1. So it's negative 1 over u. So in this case, it'll be negative 1 over x minus 1. Oh, forgot the 2. And then minus ln of x plus 1 plus c. All right. This was my final answer. Again, the integration part, simple. It's really just the LNs and stuff. It getting to the integration part, that is the hard part, and the part that's going to take you some time. All right, got one more method I'm going to show you. Yes, there's 4 cases, but the 4th case is basically a repeat of this case with the next case put into it. So it won't be too bad. And I've had so many slides, I've had to make a second section, which is fine. All right, so case 3. And the last problem, I got x squared minus 1, which I was able to refactor out to break down into linear terms. However, if I had gotten x squared plus 1, I wasn't going to be able to do that. So we have to have a situation where, what do we do if we have something that isn't broken down anymore? So in this case, this is what we do. And actually, this works for anything, and even if it goes higher than this. You're not going to see anything higher than this, at least in this class. But this process will work. So if you notice, in this case right here, the one that's broken down, so you have the x squared plus 1. Above it, I have the linear term. I have bx plus c. So in essence, your numerator has to be 1 less than the denominator in the degree. So since my bottom is x squared, my top has to be bx plus c. If it was x to the third, I'd have bx squared plus cx plus d. You would just go 1 less. And it would just take you a little bit longer to break it out and do it out, and the integration would be harder. So we're only going to go this far. All right. Now you can see how we can start getting a lot more letters put into play, because when you have when you have a quadratic in the bottom, you're automatically going to have 2 parts on top. The one piece that's going to be important for this is if you get something with just an x on top, we're not going to be able to break it down any further to do the integral. So that rule down the bottom, that's going to be what our integration is going to be for that. And you'll see how that's used in the next problem. So you definitely want to have that rule written down.
So if we only have a dx on top,
Yeah, because remember, any constant I can pull out. So basically, if there's no variables left, that's what we're going to have there. And in most of these situations, you're going to have that thing come up because of how bx plus c is going to work. So, all right, let's look at one. All right, and this works. Not even okay. Let me think one thing. And this works anytime you can't reduce the quadratic. So if you cannot factor it down any further, you do this. Even if the bottom is x squared plus 5x minus 10, it doesn't matter. If you can't factor out the denominator anymore, there's no factors for it. This is what you want to use for it. So this is all those ones that you can't factor anymore. All right, so let's look at this problem. So notice I do not have to do long division in this problem, which is great. One less thing I have to worry about. So we're literally going to look at factoring the bottom. And this one, I can just pull out an x. So I'm going to have the 2x to the squared minus x plus 4. And notice I don't factor I haven't been factoring the tops. The only situation where you want to, if you'd want to factor the tops, is if you can cancel something out that's on the top and the bottom. So that'd be the only situation you want to factor. And in this case, once you factor the bottom, you can see if you can do that. In this case, we're not going to be able to do that. So if you factor out the bottom and you say, wait, maybe I can actually factor part of this out on the top and cancel it out, you can do that. But you don't actually have to. All right, so I've got this. So my 2 pieces are going to be a over x and then bx plus c over the x squared plus 4.
What about the extra term there, that was on the previous page? To the right of the x plus c.
Which one?
Are we gonna need dx plus c, or is it just because?
Not, this one had 3 terms. This one had 3 things in the bottom. That's why there's 3 of them. The x minus 2, the x squared plus 1, the x squared plus 4. My problem, I only have 2 parts. I have the x and the x squared plus 4. So I only need 2. All right, we get to this part. So now we got to find my coefficients. If we look at how this problem's set up, plugging in numbers probably is not going to work so well. Because first of all, there's no number that's going to make this 0. So just plugging in numbers probably isn't going to be helpful for me, except for maybe finding the A, because it'll get rid of this one. So let's look at it in terms of a system and see if it actually works out kind of nice. So we'll distribute. So I have A times x squared plus 4a plus bx squared plus cx. So my x squared term is 2. So I have 2 equals a plus b. My x term is -1, and that's just c. And my number by itself is 4, and that's 4a. So C, I'm done. A equals 1. And that would then mean B also has to equal 1.
Right, could you please slow that down?
Yeah, so basically, so let's look at this part here. So I took the coefficient from the x squared is 2. And then I looked at my 2x squared terms in the problem. So I had the a plus the b. And then I took the -1 that was in front of the x, and I looked for the one over here that had an x. And that was just the c. And the same thing for the number at the end. That was the 4. And the only thing that had no letter on it was the 4a. And then I solved the ones that were simple. So C was already done for me. There was nothing left to do. A was simple enough that I just divided by the 4. And once I had the A, the first one, it was 1 plus B, so B had to be 1. That makes sense? So sometimes I didn't have to do systems in this one. It's in essence set up as a system problem, but I just didn't need to use a process for it. Sometimes it's that simple. Sometimes it's not. Sometimes you would have to actually do the systems out. I don't believe the ones on the tests will have anything crazy in systems wise to do it. You should be able to either do it the way that I showed you before, or it'll work out pretty nice like this. So.
And so now we're breaking out x terms based on their powers as well. So if we had x to the third terms, we would have broken that out from our original equation.
Yes. Yep. So this is actually the way that I did the very first problem before I did this, showed you the other way. It was, we set up the actual pieces and matched them up to the coefficients. Both ways have its benefits. The other way is really quick and easy. if you can find the numbers to get rid of things. And this one, the x squared plus 4 would never have gotten rid of anything. So I wouldn't have been, I would have had to pick a couple of numbers to make it work out. So. All right, so I'm left with this. So A was 1, B was 1, and C was -1. So I got 1 over x plus x minus 1 over x squared plus 4 dx. So we're going to split this up a little bit more. So I'm going to split this up like that. And then I'm going to split this up like this. And then I'm going to split this up like this. So the goal with all these is to get it down to a simple thing that I can do my integral for. So when I have a numerator, I can split that up. So I have the x minus the 1. So I can split that up into the x over the denominator and the 1 over the denominator. That I can do. So the 1 over x is just ln of x. This one right here, I can actually do my u substitution on. So I'm going to make my u x squared plus 4. So du is 2x dx. So it's 1/2 du equals x dx. Notice I have my x up on top. That's what allows me to do my u substitution. So this problem becomes the 1/2 1 over u du. So it's 1/2 ln of u, which is 1/2 ln of x squared plus 4. If I didn't have the x up there, I wouldn't have been able to do this u substitution, which we're going to see in the second part, the other part of this problem. All right, now remember the Alamo. No, okay.
Oh, this isn't my US history class, is it?
All right, remember this trig rule that, or this little thing with the trig problem in it that I said make sure to write down because it's going to come in handy. I've got it here. I've got 1 over an x squared plus 4. I can't do this problem out. I need to use this rule here. So the answer to this problem, that 1 over a, in this problem right here, my a is 2. Because that's 2 squared would be the 4. So this problem is 1 over 2, the arctangent of x over 2 plus 2. That's how you'd write the final answer.
Are we going to actually go into the process of understanding why that's true?
No. And actually it's because I don't know the proof off the top of my head. So I would actually have to look up the proof to be able to explain it to you. I don't know that proof off the top of my head, so.
That's the class you were talking about. That's after linear algebra, right? Math theory.
Real analysis is basically the proofs of a lot of the calculus functions. But real analysis is more the proofs of like integration by parts or partial fractions. Like I learned how to prove this concept of being able to do like the A, the B, the X and all that stuff. I didn't learn how to prove every little trig identity though.
We'll leave it for that class.
Yeah. I know my limits. It's like there's some things that, yep, just I probably could look up and actually be able to explain it once I read through how to do it, but I don't think most of you really want that. Unfortunately, the sum identities you're just going to have to remember. It's kind of like it's just write them down in the notes, use them, look them up in Google when you actually have to do this in the real world. So, but as you can see, the integration is pretty straightforward in this one. It's just the LNs. The one thing I did want you to notice was that this one, it's not a crazy, it's like, it's not one, or you still have the LN because this whole thing inside is your U. So. All right. Since we're getting really short on time, I'm going to show you two little things. I'm not going to do it. So this is the first one. I did remember I said if the exponent on top or the degree on the top is higher than the degree on the bottom, you have to do long division. You have to do it even if they're equal. So even though this one is equal, you still have to do long division to break this one out. Not doing that right now because we have no time. And the last thing I want to show you is the case 4, which the reason I'm not going through and doing this one is it's basically case 2 and 3 put together. If I have a quadratic factor that's repeatable, I have to do the same thing that I did in case 2. You'd have to break it up. So like if you had 3 of them, it'd be that one squared, that one third with the A plus B, C plus D, D plus E, and it just keeps going. So show you an example of that one with this one. So if I did this one, it would be A over X plus BX plus C over X squared plus 1, and then plus DX plus E over X squared plus 1 squared. So you'd actually split it up like that. So it's kind of the combination of case 2, where we had multiple linear factors, we have to write them out and do the squares, and case 3, where it's the BX plus C on top of it. I will have the notes for both these. When I post the notes online, I'll actually have the solution done out in it. I'm just going to copy and paste it from the book though, so you can see exactly how they work these problems out. All right, that's my time. Tuesday's the review for the test. Don't freak out. Like I said, this test is probably the hardest one. Chapter 7 is hard. But going over the review, it's already posted on a WebAssign, so you can do it as many times as you want. I would highly suggest doing that. We'll go over on Tuesday. If you have specific questions, if you've done them out and you have problems and stuff like that, if you want to send me a picture of them, I can actually go through it. I can show you where your mistakes are. That's not a problem. I can do that right in class if you don't mind me using your example. I won't tell you who it was. But this way, it's sometimes nice to see mistakes that are made for the rest of the class, because that prompts you to make sure that you pay attention to those situations. So if you don't mind, if you're doing them and make mistakes and can't figure it out, send them to me. I can use them. But we'll do that. And then Thursday is your test. It's going to be on Zoom. The way the test works is I'm going to basically throw you all into separate rooms, breakout rooms, and you'll just have your camera on and share your screen. So this way I know you're taking the test and I can see what you're working on the computer screen. So that's how the test is actually going to be done.